Hi, everybody. My name is Paul Taylor. I'm a senior engineer at NVIDIA. I work on the RAPIDS team. If anybody's familiar, it's NVIDIA's data science libraries. So if you're familiar with Python or the PyData ecosystem, you might be familiar with a lot of the concepts that I'm going to go over today. RAPIDS is sort of NVIDIA's version of like our GPU accelerated PyData libraries. So if you're familiar with pandas, we have a similar library called cuDF, the Cu data frame. If you're familiar with scikit-learn, we have a similar library called cuML. If you're familiar with NetworkX, we have a similar library called cuGraph. You might be noticing a theme, everything's Cu. That's just what NVIDIA does. All right, so are we mirroring? We good? Is that, that's too, yeah, that's a little too small. All right. Also with this. All right. Right, there we go. Perfect. Just a quick check that everything's working good. It is. All right. So I was going over our data science libraries. So NVIDIA Rapids is just a suite of data science libraries. They're mostly in Python, although we're starting to see some adoption from the Rust community, or we're building Rust bindings to our libraries. All of our libraries are written in C++ and CUDA, and then we have higher level bindings on top of them. So a number of years ago, I also worked on some experimental node bindings. Who doesn't love Node? And so it follows a similar model where we have a C++ library at the bottom, and then high-level language bindings on top. Unfortunately, though, I think a lot of people here typically access the GPU through their browser a lot of times, and so unfortunately, that's not really a mode that we can help with much. CUDA doesn't run in the browser, and NVIDIA writes everything in CUDA. So until someone decides to port CUDA to Chrome or provide a CUDA backend for web GPU, it's not going to be that easy to just take CUDA programs like TensorFlow or PyTorch or cuDF and just run them in the browser. However, that doesn't mean you can't get the advantage of using CUDA to accelerate some of your browser workflows. And so that's some of the stuff that I want to show today. I started this, what got me on this topic was someone joined the company earlier this year, and he essentially was 2 or 3 weeks in and was like, I've got this mandate, I want to do this thing. And this problem that was really fascinating, really interesting was, we've potentially got these single cell genomic plots that could potentially be up to 1 billion points. And so, if you think about a scatter plot, potentially 2 or 3D, whichever one, but 1 billion points, and you want to make that work in the browser. Because that's, even though we use CUDA on the back end, and we use CUDA through things like Omniverse, and sort of think about data science like GeForce Now for data science kind of stuff, we're using back-end rendering and streaming it to your iPad or something. A lot of people still just access stuff through GL or web GPU just through Chrome. And so that got me thinking, it's not my main project. This is really just a labor of love. Mostly these days I work on back-end build stuff and been writing some Rust. But this was just sort of a side project, and I'm excited to come and show you guys some of what I whipped up. So the idea is, just before we start, the New York City taxi data set is one of my favorite data sets. Just because it's an easy data set, it's got a lot of data, it's all real, there's a lot of things to correlate about it. But even just if you want a ton of data just to plot, it's fun. And so one of the libraries that I worked on in Rapids is our geospatial library called cuSpatial. And so that's a library that's similar to GeoPandas that takes a lot of these common vector-based geospatial algorithms and ports them to the GPU. So you think things like point and polygon hit testing. We've got a quad tree implementation that I'm going to talk a lot about today. You've got distance calculations, typically all vector though, where QSpatial doesn't really deal with raster. There's other libraries on the GPU do a lot of raster stuff, so that's really not what QSpatial wanted to focus on. And so this original problem got me thinking, how would I go about putting 1 billion points in the browser, right? Obviously, if you just got XYs, you're talking about downloading 4 gigabytes of data, and that's not really feasible. And so, let alone like having your MacBook Air render that. So, and a lot of the strategies that I would typically use in CUDA, MIP mapping or whatever, aren't available as easily unless you got the data there locally, right? You got a lot of GPU memory. So that brings me to why I have this guy and why I have this project open up right here. And unfortunately, this project did break this morning, and I'm not sure why. But luckily, I have a backup. And why is this not? There we go. Luckily, I have a backup project that shows all the same things, but not quite as pretty of a viz, but it's functional on the back end. So what are we doing right here? All right, so this project, what I have right here is I have a front end that uses deck.gl and a back end that's written in Python. And what I just opened up VS Code in is this little utility. You might be familiar with the concept called dev containers. It's a thing they built into VS Code and code spaces. So if you're familiar with GitHub code spaces, it's what powers code spaces. It's essentially a Docker container with a bunch of configuration. So they built it right into VS Code. And so I can configure VS Code to open up a Docker container. And that's what I've done. So this JSON file says, when you run this Docker container and mount in GPU device equals 1. So that's why the window is much smaller. There we go. Now I can see my stuff. All right. So if I open up, I'm inside this Docker container, and sure enough, I can see this RTX A6000. This GPU, it's a pretty big GPU. It's got about 48 gigabytes of memory. It's not anything that you couldn't go buy yourself if you wanted to spend a bunch of money on a GPU. But that's actually why I bought it. Is I like this setup because you don't really have to have a fancy machine. Like this laptop isn't super great, compared to this GPU, but I can get a lot of really good work done just by having this little enclosure here. So before we start, I just want to show you the end product because that'll show you what we're all working towards whenever I start boring you with all these details. So I've got this little web server here, and I'm going to start it up in HTTPS. I just made some local certs, and I installed a certificate authority on my machine, so I can now open up this. And this is, if you're familiar with New York City, this is just a small subset of the green taxi rides in August 2013. This is the part that broke, unfortunately. This is the yellow cab rides. So the data set's, oh my God, it's not broken. Wait a minute.
I think you just need a different power supply.
It was definitely a power supply. Sure. Or the resolution maybe. Okay, so this is awesome actually. So this data set, and the reason I love this data set is, and I just want to show you this real quick. This data set right here, I've got all the data that I was able to find with lat-long data. Now they've got it anonymized based on which pickup and drop-off location, like which region they were dropped off. They don't give you the actual point. And I want the actual point because I want to plot everything. So I've got these years for yellow and green cabs. And if we look at the sizes of them, I've got 181 gigabytes of CSVs here. Just because I want to make this as general purpose, like this is a normal problem to have. Everybody has data like this. It's messy, it's in text formats, it's unoptimized, it's really difficult. And if you want to, I've got gzip CSVs, and it gzips down to 40 gigabytes. So not that bad, but it's still CSV format under the hood. So the first thing I do whenever I start a problem like this is I say, how do I get this data into a format that I can use, in a format that I can send to the browser, in a format that I can work with on the GPU? And the very first thing we do is we parse the CSV, turn it into some binary format. I'm very familiar with Arrow because I worked a lot on the JavaScript implementation of Arrow. So I like to take data and immediately go to Arrow. So if we look right here, I have some little services that can read these tables in. So I've got my zones, my taxi zones, and I've got my taxi rides. And I've just made a little class here, and this little class just encapsulates some logic about what we're going to do with these data sets. So I've got the very first function that I wrote was this data set to read the ride CSV and then turn it into an Arrow file. So what do we need to do if we're going to read the CSV? Obviously, we need to read the CSV. Its schema is a little different based on whether it's a yellow or green cab. But essentially, then we can just call this read CSV function. And I was a little tricky. This PD right here, most people would say import pandas as PD. I like to do that because it makes things normal. And cuDF actually has a pandas mode. So if you've got pandas code currently that runs on the CPU, without changing the code at all, you can make it run on the GPU. So I like to still write code in this style because I'm used to using pandas like this. But really, just know that this is actually calling a GPU function to read the CSV. So the zero code change, by the way, is like python-m cuDF.pandas and then your script or your program. So it's really like you don't even have to modify your code. So that's kind of neat. In my case, what I do is I have a little wrapper here that says, hey, I'm going to read this environment variable. And if we say use pandas, then I'll force it to use pandas. But if not, I just import cuDF because the APIs are very, very close. So the first thing that I really do is I read the CSV. Then I've got to clean the data up somehow. Like I don't care about most of the fields there. I don't care about them. I want basically the X, Ys, and maybe like whether it's a source or a dest. If you might care about more fields, in which case you do something else. But then essentially I just clean the points. There's some messy data. I query the source and dest because they're outside of the range that I care about. They're outside of the taxi zones. Maybe they got dropped off in Westchester. I don't personally care about that for this demo. Then I essentially combine the points into one data frame because the source and dest are 4 different columns. And I want to just make it a single table of XYs. So I get one giant table of XY columns. And if I want to add a third column of like a Boolean, whether it's a source or a dest, because then I don't have to spend 4 bytes, to say whether it's a source or a dest, or 8 if you've got them in separate columns. I can encode that in one Boolean. And lastly, I'm actually, in this case, I wouldn't normally do this, but because I'm doing this for this demo, I want to filter the points and get exactly the ones that are in the New York City taxi data set. And how I'm going to do that is I'm going to use cuSpatial, and it's really fast point and polygon hit test using a GPU accelerated quad tree. And so this quad tree I'm particularly proud of because I worked on it a lot. It was an implementation of a paper by a researcher in New York at City University. And at the time, it was the fastest quad tree in the world, at least for building. There's since been a quad tree, or it's an R tree really, that uses the ray tracing, the ray tracing hardware in the modern GPUs. So maybe one day we'll throw that into cuSpatial, but today, as far as I know, it's one of the fastest quad trees in the world. And what's neat about this quad tree is it's a point quad tree, so you can give it just a ton of points and say, I'm going to throw all my points at it, and it's going to distribute them all in buckets all around the city. And then I'm going to take my polygons, and I'm going to search the polygon. Like I'm going to search in parallel each polygon, and it's going to filter down and return me the points and which polygon they were in. And sometimes the polygons might overlap, but you can throw a lot of polygons at it before it starts to saturate the GPU. So that's essentially what I'm doing here. Is I've got a little class here. This little class takes the points. And this class, I wrote it, so I made it take a set of projected points because I'm dealing with lat longs here. And I want to stay on the GPU as much as possible. And I want to do the thing that's fastest for the GPU. 64-bit math is not the fastest thing for the GPU. So I would like to stay in 32-bit land. But if we've got New York City, the lat long for New York City is like -73, -74, a lot of decimal places. we can't deal with that on the, that would, the quad tree gets distorted. So what we'd like to do is project it into something like centimeter or meter offsets from like the middle of New York City. And so I made the quad tree, behave that way. It'll performance calculation on the projected points, but then give you back out the lat longs. So it's just a really fast little transformation, but you'll see me doing that a lot. So right here, we build the quad tree, then we search the quad tree for our taxi zones, and then this gives us back out an index of all of the points and which polygon they hit. And in my case, I'm just saying take all the original points and do a gather call for the points that are in any polygon. I don't care about which polygon they were in. I just want to make sure they were in a polygon. And then essentially what happens is this data frame right here that comes back out will have only the points that are in the New York City taxi zones. And then finally, that's it. That's how I convert my CSV into an arrow file, or at least into a GPU data frame that then I can very easily copy back and post and turn it into an arrow file. So that's essentially the ETL part. And that's how I took all these CSVs and I turned them into $33 GB of arrow, which is great. Like it's even smaller than the compressed CSV, and it's just floats, but it's still better. So now that we've got the data already converted, the next thing we want to do is actually write a server that's going to use any of this data. We want to actually plot this and get this down to our end users, and finally solve that problem of how do we show something like 1 billion points or even 100 million points in a browser. So that's where we start writing this little server. And so I've got just a little Quart server. It's a little Python. It's Python Flask is a library, a HTTP server in Python that's really popular. Quart is like its big brother or sister or evolution that deals with all async IO. And so I just like using Quart because it's super minimal. And so what happens with Quart is you just say, here's a route, and here's an API v1 and a route for v2. And I've got my routes here. Here's my v1 routes, and here's my v2 routes. And I'll show you why I've got v1 and v2 routes. And then anything that in v2 that doesn't match, that wasn't matched, I just redirect it to v1 because I didn't change that API. And then finally, I have this little index.html file here. And this little file is not complicated at all. It loads deck.gl, it loads Arrow, it loads MapLibre. And essentially, it's just got the checkboxes that we're looking at right here. So all it does is it's got a layer for the GeoJSON. You can see I've actually got 2 layers here. I've got one layer for the GeoJSON, which just loads the literal GeoJSON file. And then I've got another layer. This would be the GeoJSON layer here. And I just say its data is going to be the New York City taxi zones GeoJSON, exactly as if you downloaded it from New York City. But I also wanted to show off, in case anybody's not familiar, on the server, we're going to be dealing with some polygons, right? The New York City taxi zones are a set of polygons on the server. And so ideally, we want that to match as closely as possible to what the UI is seeing. So the goal is like, what happens if the polygons on the server are in 32-bit and the ones we're getting in the GeoJSON are in 64-bit? There might be some, some distortions, some points that are inside or outside some lines on the UI that we wouldn't necessarily understand why. So I wanted to have this, 2 layers. Essentially, you can toggle it on. You can say, show the zones as if you've downloaded them as a GeoJSON file, or show the zones in the arrow format that the server's using, because the server can just send you its arrow format. And so that's all this little toggle is doing right here. Then I have these other 2 toggles which decide which trips data sets to use, and you can actually have both of them on. And then I have a start data set and a start date and end date for my data set. So the reason I like this is I can say start at August 2013, and let's look at what's going on between August and December. And that's a lot of trips between August and December for the green caps. And I like it because you can just go and see progressively, more and more and more data. So what's going on here in the UI? What we're doing is we're saying, if these toggles are set, then show the rides layer, use the GeoJSON or use the arrow layer. The rides layer is a tile layer. So here's where I started thinking about the billion points problem. So if we're sitting here with a billion points on the back end, and we don't want to send all billion points to the front end, we do what Kyle was talking about, where we essentially do tiling on the back end, and we do some filtering step beforehand, and then we use something like the tile layer here to load that data dynamically and in pieces. And so as I've been mousing around here, I don't know if you've been noticing, but that's essentially what's going on. Is we've got this tile layer that is querying the server on the back end for the points that are in each tile. But along that, it's also sending a level of detail, and so the server is able to filter out, essentially do a map, texture min filter on the points before it goes down to the client. Because these points, these arrow files are 400 or 500 gigabytes per month. And so I don't want to send 400 or 500 megabytes per month. So I don't want to send potentially, 2 or 3 gigabytes of data to the client. Yeah, that's where, now we're seeing a mess up. Okay. So the strategy here is take the tiles from the UI. It's sending you, each tile, and it's sending you its, lat long coordinates. Turn those into my projected coordinates that I'm using in the quad tree, and then query the quad tree with just those rectangles, and just say, give me all the points that are in each rectangle. And so that's essentially what we've got right here in this service. I'll stop this and show you what would happen if I was running this in HTTP1. So we're looking here. This is this implementation, API v1/rides, and it takes a tile ID. I have the UI is able to send the range of dates it wants, and then each taxi type that it wants to render. And so I've just got a little class called tiles, which just represents a list of tiles. I've got my taxi zones. I can just read them as float64. And then I've got this function which will read a list of these arrow tables by date. So I've got, it'll read yellow and green, and then from 2010 to 2012, whatever the coordinates or whatever the dates the client sent. And it gives me those back as lat longs. Of course, I can't really use the lat longs on the server because they're too close together. So I need to project them into kilometer or meter or centimeter offsets from the bill of New York City so that I can do a fast operation with the quad tree. So I can project this here using cuSpatial again to do that sinusoidal projection. Then I can construct my quad tree here, and again, since it's sinusoidal, we need the origin so that way we don't get stripped. And then I can do this point and polygon hit test, and essentially have to do that same sinusoidal projection for the tiles, but pass the tiles in as the rectangles to do the hit test for, get back out the point indices, do this gather call right here to get the centimeter offsets. Then here's where the fun filtering comes in, is we've got each tile has a level of detail. And so it's a really easy function to write, is this little min filter, nearest filter, sort of texture mix. So with this data set, this is my data frame of XY columns. And so I just save him out right here, and I save him. So now he's got X, Y, and then index column. And then in a loop, just while level of detail is less than max level. So level of detail can be 1 if we're super zoomed out, or positive 20 if we're all the way zoomed in, we want all the data. All we do is divide the points X and Y's by 2, and then drop the duplicate points. Because that'll essentially force all the floats onto the float grid, and then we drop all the duplicate ones. And so we do that in a loop, and eventually we get a much smaller set of points. And then we just return that index column right here, and which we can then just use to select our original points, the lat longs, just do a gather call for those and send those down to the client. So we took 2 million or 25 million points, did that min filter, got the indices of those, and then we did a much smaller selection of the lat longs. We sent that down.
So you're not sending a tile to the browser, right? You're sending.
Aha, no. So that's where let's look at this. This is actually what I want to do. HTTPS. All right. So here's the next trick. Here's our Chrome inspector. And so for each of these requests, it's making this for API/v1/rides. And it's not too shabby. Like these are small, 400 bytes, 557 kilobytes. If I was to switch this over to the yellow cab dataset, still pretty quick. One of the tiles is 1.5 megabytes, but that's pretty good. And so here's the thing, though. I switched. So I didn't really call this out. I switched the server from HTTPS to HTTP. This is part of the what I wanted to show off for how to fully utilize the GPU. So when we're in HTTP, we can't use HTTP2, and so we've got a max of 6 requests in parallel at a time. And we can see that in the lag here as we're loading points in. Takes a while for these points to go and update. As we're browsing around, it takes a long time. And so if we've got a bunch of points we need to load in, a bunch of tiles, it's not ideal to be using HTTP1. And also the other thing about it is, let me go change something in the server. We're actually being less efficient on the server. So because each request has to come in individually, we have to query the quad tree individually for a single polygon, a single tile. Whereas the GPU is way bigger. It can query hundreds of millions of points with thousands and thousands of tiles. So, but by forcing us to use HTTP1 this way, we're using the GPU almost as inefficiently as possible. And so I'm actually timing that right here. So right here is the total aggregate time it took. All this is the time we took to query the quad tree, total aggregate time, just to get our XY coordinates for the initial page load. So you can see it takes almost a second to get the tiles for a reasonably large data set. But by switching over to HTTP2, all of those requests can be batched, and then we can dispatch them to the GPU all at the same time in one call instead of 6 individual calls. And so it really makes a difference. I'm going to show again the same load, but using batch mode. It's not 8080. Here we queried 6 tiles in 62 milliseconds. So instead of a second to get all the tiles, we were able to do it in 62 milliseconds and return those all to the browser. So anytime you can use HTTP2 to then make your GPU faster is a win. I think that's kind of all I had. These are just some strategies that I found for, if you've got the data on the server, you can use a bunch of server strategies or data science strategies to make your GPU accelerated, to make your geospatial visualization GPU accelerated, even if the front end isn't running the same software. So
what are you returning in terms? What are you doing with the coordinates that you return to the client?
So the coordinates I'm returning to the client, I'm just plotting. So each of these coordinates is an XY. And then so with court, you decorate a route, this little Python function decorator. This says court will match this route. I have a little decorator here that takes the return value of this function and automatically serializes it to arrow, and then sends that down as an octet stream content type. And then on the client side, what we have here is, so the rides layer, for example, it's a tile layer. It has this load points for tile is its get tile data function. And what it does is it takes which taxi data set, which year, and which month, or the list of those. And then it makes a request to API/v1 or v2/rides. That's going to be an arrow table because I wrote that endpoint. And so I know here I can do the fetch and then get this back out as a stream of record batches. So on the server, I can tune this, but on the server I've got it just set tuned to take my table and chunk it up in 10,000 row chunks So that way, both I can use async IO to sort of, I'm not blocking if one client is requesting just a massive table, handle all the requests. It also makes the UI a little snappier. So this just says load points for stream. What it does is it loops over all of the batches asynchronously and then yields them all to deck.gl. I've got a little custom deck.gl buffer update function that essentially grows a GPU buffer in place and then writes the points as they come in. And just as a little optimization for the UI. And that's kind of all it is.
You have this somewhere public?
Yes. So I was going to show, the one I've got currently is the older demo that I didn't show right here. This one. This one's the one that doesn't use the base map, doesn't use the lat long coordinates. This one's purely just an orthographic view with polygons. But it's the pure, like the test data set we use for cuSpatial. And so since you run the same command over here and load up my browser, it's 444 for this one. So you see no base map here. But for V1, this is even though it's HTTP2, it's still using batch. It's not using batched mode. But when I switch to V2, essentially made, whereas the first one took 361 milliseconds to do all the queries for the non-batch mode, this one took 40 milliseconds to do all the queries for batch mode. So I don't know. I like looking at points.
That's pretty cool.
I like zooming in and saying, I'm not doing any 64-bit points. There's rounding errors in here. You can definitely tell when you zoom in to the streets. You get to see the float grid. But if we're just looking at the network performance, it's decent, right?
When
6 megabytes.
On your map function, you were basically dropping duplicates.
Yes. Yeah. No.
Is it possible to sum instead of drop, so you could kind of style by number of points in that location?
So you can do anything you want. Absolutely.
Not always.
So this is all
that GPU you can, but
all the data frame library. Well, this demo actually runs pretty well on this little laptop, which only has 12 gigs of memory. So. All the data frame functions, almost if you can find it in pandas, you can find it in cuDF pretty much. And that's how we're able to make it zero code change with cuDF pandas. And the neat thing is that we also have JITting from Python code into CUDA code. So if you want to write a little CUDA kernel, but you don't want to go actually figure out how to use NVCC and how to write C++ in CUDA and figure out warp, synchronization and all the stuff that goes along with that, you can just write a little Python function that has some globals available to you and then can take some arguments and return some arguments. And that can automatically get JITted into a CUDA kernel at runtime. And so that's something that I didn't really call out, but I did do that a little bit. There's a query function in cuDF. It's not exactly SQL, it's really Python, but you can pass it a Python string that you can access your columns by name, and you can do basic operations like column A is less than or equal to column B, and get back a Boolean, or column A times column B, that kind of stuff. I'm gonna do somewhat complicated SQL. Yeah, that's it. I don't want to go. I know I've gone over time.
Meantime, well, you can ask a question while we do the next setup.
Well, how would you go about showing lines, so points, like taking both source and start and end of the tree?
How would I go about showing which one, like which desk source?
Yeah.
Showing lines.
Tiling.
Yeah. So things it was implicit in the code there, but the geo The GeoPandas spec has support for defining points, multi-points, line strings, polygons. And so essentially it's lists of lists of lists in arrow format is kind of the way to think about it. If I was going to do it there, you'd essentially have like 2 points together, and then you have an offset of grouped by arrow list. These 2 points is a source and a dest, and then I draw a line between them by grouping them as a list together.
But in terms of filtering whether they're visible in the viewport, what I say is if either the source or the depth is.
Oh yeah. Oh, for sure, the line. Oh, like that. Oh, that's what you meant. Yes. Yeah, you'd essentially say like, which direction is it going? Kind of thing. Is the point that's out of view, but you know roughly the direction component of the vector, so you can draw a line to it. Might be able to encode that, but it's probably the same amount of data anyway. So